Hello, welcome to this first lecture on Univariate SPM. In the previous lectures, we emphasized upon the importance of multivariate monitoring. However, univariate monitoring, where we monitor only an individual signal, is not of no use and finds utility at several places. Let us consider a couple of motivating examples. For that, we will consider this fluid catalytic cracking unit, which are used in oil refineries. You may already know, or maybe not, that these units are used to break down heavy oils into lighter components such as gasoline. Now, the plant manager may be interested in tracking the overall performance of the plant, let's say via thermal efficiency. Now, the plant load may change within some range, but the thermal efficiency may be expected to stay around some nominal values, and therefore SPM can be used to track the thermal efficiency irrespective of how the other process variables are behaving. Another scenario where SPM comes into picture is for tracking the errors of predictive models. Imagine that you have built a model to predict the value of this exhaust gas temperature as a function of the feed flow. If your model is pretty good, then the error of the model or the residuals, its values will fluctuate around the value of 0. Therefore, you can use SPM to monitor the unexpected deviations in the residuals and therefore unexpected behavior of the flue gas temperature. So we do see that we need techniques for monitoring individual signals. And the most common way this is done is via control charts. A control chart is simply a time plot of the process variables along with some threshold values or the control limits. These are called the upper control limit and the lower control limit. Additionally, on these control charts, you will find a center line, which is simply the expected mean or the nominal value of this process signal. If your process is behaving normally, then your process signal will stay within these control limits and the process is said to be in control. On the other hand, if your process signal starts showing certain drift and it breaches the control limit, then it indicates an out of control scenario or a process fault. A quick note here. In practice, the process measurements are made at discrete time intervals, and therefore this x-axis represents the sample number or the sampling instant. Now, the adjustable handle that you have during the creation of these control charts are these threshold values, and their judicious selection is very important. For example, imagine that you keep the control limits very close to the center line. What will happen? Well, you will end up with a lot of false alerts, right? On the other hand, if you keep your control limits far away from the center line, then even if your process starts to deviate, you will not get any alerts. Both these scenarios are obviously undesirable. So, in practice, what is commonly used is the 3 sigma control limits. Here, the threshold values are set at 3 times the standard deviation from the center line. This sigma is the standard deviation of in control historical samples. So, why is this done? And what are the mathematical implications? Well, as it turns out, if your process signal X follows a Gaussian distribution, then the probability of X falling outside of the control limits is very small. It is just 0.0027, which means only 0.27% of your samples will end up outside the control limits when your process is operating normally. Alright, Now you have some idea about how to set the control limits. Let us look at how the development and the deployment phase of a control chart tool development look like. During the development phase, you will use your historical samples to estimate the parameters of your control chart, which would be the standard deviation and the center line or the mean value of the process signal. Once you have estimated these parameters, you will set your control limits accordingly. You may use the commonly used 3 sigma control limits or 2 sigma. Once you have the control limits, you can simply plot the data points as and when they arrive onto this control chart and infer the in control or out of control scenario. Sounds simple, right? Now, there are three types of popular control charts. One, the Shewhart control chart. Two, the QSUM control chart. And three, the EWME control chart. We will look at all these control charts in this course. In the next lecture, we will start with the simplest of them, the Shewhart control chart. See you there then. Bye bye.